Greetings, Graham Warren, working with you on a queuing model for the neighbor's coffee shop case. Got some input parameters here. Let's walk through them. So we have the arrival rate of customers overall, two neighbors. We also have the mean order time for a returning customer of 150 seconds. The order time mean for a new customer of 300 seconds. So you can vary these. These were reported by Spencer in a recent meeting. We also have the probability that a customer chosen at random is a new customer, uh, in which case the order time new applies, otherwise order time returning applies. And then we also have, let's just try this in the base case, which is the current case. There are no online orders or QR-based orders. The reason this matters is, if we can get the customer to put the work in to place the order without pay, that frees up a barista from having to engage with the customer and then spend the time discussing order details and collecting payment and whatnot. All right, so with all of that in mind, so let's just take a step back here. If a new customer comes in, that's a 300 second mean order delay with a standard deviation of 10 seconds. Returning customer 150 with a standard deviation of 10 seconds. These are both considered normal distributions. We're taking them as normal, those order delays. And then if it's an online order, 0 time on the part of the barista. So all that comes out at 180 seconds average. So one of the techniques that we're going to use in our queuing analysis is to create sort of a proxy customer. And this idea of putting these three types of customers, new, returning, and online, together into a proxy customer, that's precisely what we're doing here. So just weighted with the probabilities in a sense. The same thing's going to happen for the processing times. So what we have in this table here are the 20 drinks that are available in the simulation model and in the queuing model. And you can see that we've got a fraction here. You can vary these. The labor mean and standard deviation, the non-labor mean and non-labor standard deviation are all changeable, but I would leave these alone unless you have outstanding information. This is typically going to be something that you're going to change to one, assess the current scenario that Spencer is pursuing with the menu that is available, and then the usage or the consumption preferences of those customers that are coming in currently. And then for your own design, where you redesign the menu and rethink the coffee shop, obviously you're going to come up with some set of probabilities that match that design, and they should total 100%. Okay, so that proxy customer's characteristics are captured here for the labor. The mean and the squared coefficient of variation are 3273 and 0.01. All I'm doing here is I'm just basically using the idea of expectation of a weighted sum of random variables is those weights times each of the expectations. And then for the variance of a weighted sum of random variables is the squared weights times the independent variances. And we're assuming all of these are independent. So the labor is pursued at the rate of 32.73 per hour. That's the rate at which. So overall, let's reframe this. So in this setup we have here, it's an espresso-based shop. It's the 100% of the drinks are espresso, and the average time for labor is about 2 minutes, and a little less than half a minute for the non-labor. So you can see that you should be able to do something like between these, something like um, 30 per minute based on, if it was 2 minutes, then it would be 30 per minute. That's where this rate comes. So the proxy drink, so this weighted average drink, whatever it is, 32.73 of those per hour are producible. And currently that's just an espresso-based beverage. All right, so then a squared coefficient of variation for the labor. We've got the same kind of calculation. It comes off of this weighted non-labor analysis. It's 144. That non-labor piece is pursued at the rate of 144 with a non-labor squared coefficient of variation of a small number, 0.04. Okay, so I've got a breakout here of imagining the process here. So this is sort of the order station, the labor piece, the non-labor piece. Now there's already an assumption built in here, and that is that when you're making one of these beverages, tea or coffee, maybe something else, that you sort of like get all the labor squared away, and then you do the non-labor. But in fact, in any beverage, there's probably sort of a back and forth where, so there's some barista involvement, and then there could be some sort of wait for a tea to steep or something to happen, maybe a mocha pot to boil, or get very hot at least, and then you go. So that would be that would be a non-labor time, but then the barista will have to come back and sort of pour the drink out and so forth. So we are assuming that these two times are independent and they're partitionable as we've gone, but that is an approximation. Okay, so we're now able to sort of like put our model together, and the arrival rate is 40 per hour at that order station. It's a Poisson process, so its squared coefficient of variation is 1. And then what I've done here is gone ahead and looked at what this mean order time is. So that's 3 minutes. So that means the processing rate of the orders is they're 20 per hour. And I'm also able to calculate a squared coefficient of variation on that. So I'm able to do the same thing for the labor. The rate is going to be the same because there's no customers lost. And we're assuming this is again another approximation that the departure process of the order station is Poisson, which it's not, because the service times are assumed to be normal, right? But it's this is an approximation overall, and we're using that approximation for the non-labor piece as well. So this 3273 comes off of here. That's the rate at which you're processing this sort of weighted average drink, whatever it is, the proxy drink, and the same for this. Now, I am able to, the barista is involved in the ordering and the labor. And so what I'm looking to do there is to sort of collapse that into, one sort of aggregate process step, and I'm calling that ordering and labor. And I'm able to put that together here. And you can see the rate's 40 again. So the non-labor piece is identical to what we had previously, but this one here is a blend of ordering and labor. So that is in essence, calculating these parameters is using things like weighted, the expectation of a weighted sum of random variables and the expectation of a weighted mix of variances. Those equations are sort of like the primary drivers along with the independence assumptions. To get the W sub Q and W sub S, I'm using Kingman's formula. And the barista utilization is simply the arrival rate divided by K times mu on this. So there is no barista utilization on the non-labor piece because guess what? There's no labor, right? But it still takes time. And so we are able to get estimates then. It's the sum of these two times W sub S plus here for the ordering and labor plus the W sub S for the non-labor that gives us a sort of the overall estimate of what a customer is going to experience from time of arrival to beverage in hand. All right, so let's play with it just a little bit. We are able to see, and so the number of baristas is spelled out here. So if I put 5 in there, you can see that I'm turning these drinks around for the customers, from time of arrival to beverage in hand of around 5.7 minutes, which, seems reasonable. What this does not factor is the number of point of sale terminals. So we're also assuming that the ordering and labor component is independent of the non-labor. In fact, the ordering and labor is independent. And these assumptions are fairly aggressive. So we're going to get aggressive estimates of the of W sub Q and W sub S. So this one here comes back at 5.7, but it's most likely longer than that because of these a violation of these assumptions that we've been making. All right, so from the perspective of trying to optimize this coffee shop using this model, I think it's a quick, it's a rapid prototyping tool. When you compare it with the simulation model that we're going to look at in the next clip, you'll probably get a sense that you're able to very quickly just make changes and get a rough sense of, 5 baristas are utilized about 64% of the time. Maybe, the question here is, can you get by with 4? So let's have a look at that. And the answer is probably, 80.56 is sort of getting onto the cusp of sustainability, questionability. But what's our wait time here? 7.2 minutes. If I go to 3, how does that look? Well, can do, right? 107, that's not possible. But how about this? We have the option of trying to incentivize customers to place the order sort of through an app of some kind. What happens if I am able to convince, say, let's say 20% of the customers to do that? So I'll go back up here, switch this out to 0.2. Maybe I can get by with 3 if they, basically pulling order commitments away from the baristas and allowing them more time to do production. So notice how it became feasible in the sense that it's lower than 100%. Now you may not love 94%. It seems like a rather long week at that level. But notice how the increase, pulling the work away from the barista, the order work, putting it on the, or having the customer assume it by entering the order, really made a difference. So, okay, let's try this 0.5. How is that going to look? Down to 74. Okay, so now I've saved a whole salary, and I've, seems like unreasonable, and I'm doing it in 5 minutes for the CX, right? So the customer experience here is primarily being measured through this quantity here, the total time from arrival to beverage in hand, and the employee experience is being measured through the utilization. This is sort of the fraction of the time, the fraction of the week that the barista is busy. And, there are going to be red lines that cannot be crossed without, seriously imperiling the longevity of that employee in the shop. Okay, so we've analyzed simply a espresso-based shop. What happens if we have sort of like drip coffees on, and let's say so you could analyze a stand. Let's suppose you're going to create an espresso stand. Maybe it's that drive-through window, possibly, but you're analyzing a stand here. So this is flexible in being able to analyze sort of standalone, specific beverage stands. Maybe they're doing 2 there, maybe lattes and seasonal lattes or something. But you could also analyze the whole shop. So now I want to look at a shop where 50% of the drinks are drip coffee. There are no lattes, but they do seasonal lattes for the rest. Now the seasonal lattes have a rather nasty, mean labor component, 5 minutes, fairly fancy lattes, about 3 times the effort of roughly of a regular latte. So the question is, can you make this go, and how many baristas do you need? All right, so I'm going to back this up. Assuming that we've got 20% new customers, and you can see I can do it with 3. Can 4 do it? Yes, at 93%. It's a 14.5-minute wait. So you're getting a sense of what these commitments are going to look like, how they're going to play out for the customer and for the employee. And all right, so can I do what happens if I got a 5 here? 74. That looks like it's livable. 7 minutes, you'd have to call that one and maybe seeing it long by some, but look up some industry standards to figure out what expectations are. Now, we did try online orders. Let's see if that makes a difference here. Again, converting work that was on baristas to being assumed by the customer. Now you're down at 66%. Maybe you can get rid of a barista. A little tough. What happens if this is at 0.3? Maybe you could allow the online orders to jump the line. That'll get more people ordering, right? Okay, so there you're at 78. So maybe you need more than this, maybe 0.5 or something. How's that? And then suddenly it's livable. So it seems like the online piece is a big one. Baristas, are salaries that you have to pay. Profit is a thing, but you want to sort of factor profit along with the CX and the EX to create a sort of a design that's going to make money, but be livable for customers and employees alike. So yeah, lots of assumptions here. When you compare the simulation, the queuing analysis that we've got here based on this proxy customer and with all the independence assumptions, you're going to find that you've got aggressive estimates of W sub S, but that's fine. Aggressive relative to the simulation that's coming in the next clip. That's fine. Awesome. Looking forward to seeing what you do with this.